All right, hello everybody, welcome. First, a few announcements. We have exam 1 on Wednesday, 12 to 2 here in class for most of you. And I should also say that okay. So for all of you who haven't received explicit permission, you will all be taking the exam in person here. This is actually going to be a written exam. I don't know if you remember those. So there'll actually be paper, you'll have to write on them, and then you'll hand them back to us and we'll scan them in and then grade them again on GradeScope. Okay. So the exam is closed book, closed notes. I think you should not need, I'm aiming for the exam to be at a level of difficulty where the grading and everything should be calibrated for when you don't have access to notes. For the most part, you don't have to memorize the details of what you did in class, but as long as you kind of understand and remember the main ideas and concepts, you should be fine. Okay. Some of you asked for solutions to the practice exam, and they will be posted today. I asked the TA to do it, and I think the TA is going to do it today. Yeah? No cheat sheet, no nothing. Yeah. And there'll be about 10 objective style questions, like true or false, multiple choice, explain in a sentence what this means or what you think it is. And then there will be 5 sort of easy to somewhat medium difficult problems. But remember, all of these will be easier than the homework, or at least easier given what you did already in homework. Okay? Any questions about the exam logistics? You can also keep the chat window open. Okay? And I'll post the homework on solutions today after the deadline. And you should have access to them as well to review them before the exam. And there's an important thing, as I said last time, since we're having the exam in class on Wednesday, I will be teaching online on this Friday. Forget the time. What did I say last time? Yeah, 2 to 4. Okay? On the usual class Zoom link. All right. So with that, let's now move on to the lecture. And exam 1 only covers the last 8 lectures. So what we're doing today is not directly going to be covered in the exam. All right. So last class, we introduced this beautiful world. That should not be a word. Well, it's a beautiful word, but world. It's a beautiful world of non-determinism where, we somehow explore many things in parallel. And it's a very powerful concept. One of the most important challenges in science as a whole have to deal with how much power non-determinism actually gives us in various models of computation. And as a legacy, I think that was probably the most important contribution of the notion of finite automata. They are useful for all kinds of practical scenarios, but studying them lets people to come up with this non-determinism as an abstraction, which is very powerful. And we also saw it in evidence, right? We saw how to use non-determinism to solve concatenation of DFAs in and also how to use non-determinism to compute clean star of languages that are themselves computable by DFAs, right? Okay, and there's a question in the chat, is today's lecture content going to be on the exam? No, what we're going to do today is not on the exam, not on this exam, it will be on the second exam, okay? All right. And what we're going to do today is, we'll do a couple of more examples of NFAs and then start studying the properties of NFAs. What are the, when we started DFAs, we looked at what they can compute, Are they closed under some various properties? Let's study these questions for NFAs. And the elephant in the room really is how powerful are NFAs as a model as compared to everything else that we've seen. Okay? All right. So, okay. Let's get started. So there are some excellent questions on HSTEM. Please keep asking them there. I usually try to answer them within an hour as long as I'm awake. And one of the questions asked there was, what happens if you have a chain of epsilon transitions in the definition of NFA? It's an excellent question. Let's do an example to kind of understand this minor nuance in the definition. Okay. So what's in NFA? Right. So recall, NFA is basically defined by a transition function, which, as before, took a state and a label, right? But then it gave out an element of the power set of C, right? So it listed out all possible, a potential set of possibilities that you could end up in after taking this transition, right? And that's what we started out with. And then we also had this epsilon transitions combined with a set S of accepting states. One way to picture the best way to picture NFA is to actually draw the diagram. And formally, you had to write like the transition table, right? You'll say state 0, 1, epsilon. You'll say state 0. What is T of 0, 0? This is going to be some set, right? Okay. And the computation was every time you read a bit, you branch along all this multiple paths. If there's an epsilon transition, you keep doing that. And then you accept if you end up in an accepting state in any of the universes. Okay. So that was the definition of NFA, and we saw how to use that to construct construct a recognizing NFA or Klein star. Let's do one example. Let me call it N3. I have state 0, which is a start state, and maybe this goes after epsilon to here, and 0 stays here. Okay, I'm just drawing something here. All right. Okay, so this is our diagram, and remember there were 3 essential differences between NFA and DFA, right? First, NFA can have multiple edges with the same label out of any node, and the epsilon transitions, and there could be some edges missing, right? Those are like these dead branches that we were seeing. Okay. Suppose if this is my NFA, and if I see the string, my input is 1. What happens? Yeah? Oh, sorry. Yes, thank you. Yeah. The names of the states should definitely be different. There should not be any ambiguity there. Thank you. Okay, so if input is 1, what happens, right? So if you look at this diagram, when the input is 1, you're starting out in the state 0, right? But before you even read a bit, there is an epsilon transition, right? So you immediately create a lateral branch. Okay, but do you stop here? No, there's further epsilon transition, right? So you have to chase all the epsilon transitions until you see a repetition. Okay, so from 1 also there is an epsilon transition, so I create another branch. And if there was an epsilon transition from 3, I would also create a multiple branch there, right? So the start node itself is kind of creating 3 copies of itself. Yeah? Right, so you basically don't repeat any node when you're creating these branches, at least in the epsilon world. Okay? You keep chasing the epsilon transitions until, like, as long as you're seeing new ones, you add them. If you're repeating stuff, you don't. It's part of the definition, yeah. It's a good question. Any other questions? Okay, so now we see the first bit. So this is happening before we read the bit 1. Okay. From 0, if I see 1, I end up in state 2. Okay. And if I'm in the state 1 and I see a 1, nothing happens, right? Because that's a dead branch. There's no 1 edge. That means the simulation of that particular universe has terminated. And when I'm at 3, I see a 1, I go to 4. Okay. And this is an accepting state. All right. So M3 of the string 1 is actually 1. So when you see the bit 1, the output is going to be 1. Because after reading the bit, we have 2 branches, 2 alive branches. And in one of them, you are in an accepting state. So you say, I'm going to accept the string X. All right. Any questions? Okay. And you keep doing this multiple branching, even if it happens sometime later in the input, right? So in this example, the epsilon transition, there is a chain of them right at the beginning, okay? But what if the input was, maybe the start state was, the epsilon transition was not immediately at the start state, but it was later on. You do the same thing. Wherever you are, you always chase out all the epsilon transitions and then start reading the next bit. Okay? All right. So that's that. Let's see one more example of why NFAs are so useful in kind of designing diagrams, right? Making up this diagram. So I'm going to specify a language, and hopefully you'll come up with a nice way to recognize that using a DFA or an NFA. So what's the language I have in mind? All strings that have a 1 in the last 3 positions. Okay. In other words, the function in the equivalent world, the function I'm trying to compute is f of x is 1 if x has a 1 in last 3 positions and 0 otherwise. Okay. So for instance, f of 1, 0, 0 f of 0, 0, 0, 1, 0, 0. These would all be accepted, right? Whereas something like, there's no one in the last three positions, right? These would be not accepted. So the output on those strings should be 0. On the other things, it should be 1. The question I'm asking you is, can you design a DFA for this language or an NFA for this language? You might first think of trying to design a DFA, and let me tell you, it can be done, but it's a bit messy, because somehow you need to figure out, right, when you start reading the bit and you design a DFA, you don't know when to start looking for the end. You cannot go back, right? So how do I know if I've reached the end? And based on that, I need to immediately say something, right? So that makes designing the DFA tricky. But if I ask you to do an NFA, how can I do it? Any suggestions? Yeah? Okay, so you record the last time that 1 appears and then do what? No, but we can't go back, right?
Yeah, but like, after 0, then it goes to the next stage.
Maybe, but let me tell you that DFA, designing a DFA for this, what you're saying is going to be DFA, right? Is a bit tedious and messy. Because somehow what you're saying, I think, would work if it was something like, okay, does the first 3 bits have a 1? If it's in the end, then it's a little complicated. But let's try to do what you're doing, but let's use the power of non-determinism to help it along. Okay, any guesses? Any ways to exploit non-determinism to make it very transparent as to what's happening? Yeah? Okay. Let's see. So this is the start state. It's saying put 0, 1, 1, and then what? Epsilon from 3 to 0. What's the accepting state going to be? 1, 2, and 3. Okay, let's see. I think this will work, but let me change it a little to make the argument a little cleaner. Okay, so instead of putting this epsilon edge here, I'm going to make a small change, which is okay. So the only change I put here is to make why you're putting the epsilon arrow there a little clearer. So what this diagram is doing is trying to just guess when you're going to kind of say I'm reached the end of the string, right? So when I'm close to being in the end of the string, I'm going to start checking for 1, right? But before that, I'm just going to keep looking at the same state. Once I take the epsilon transition, the only way I can reach the accepting state is if I just end up within this within 3 steps of the end. Okay. Whereas otherwise, I keep looping here. So for instance, if I see the string 100, what's one accepting path to it? I first make the epsilon transition right away, and then I read 100, I have accepted. Okay? Otherwise, I haven't. So for instance, this, let me call this N4. Right, I start with 0, but then I create this copy, which is a 1, okay? And then I follow 100. I'm going to ignore what happens on this branch. It's not particularly important right now, but when I see 1, I go to 2, I see 0, I go to 3, I see 1, I go to 4, which is an accepting state. Okay? So accepted. Whereas you can also check that when I'm not, if I have something like 1 followed with 3 zeros, I'm never going to accept. Because I have to take the epsilon transition at least once to reach an accepting state. And once I do that, I cannot read more than 3 bits. Or if I see a 0 there immediately, I'm dead. Yeah? 4 ones. Sure. So a lot of stuff happens, you know, there's like a lot of branches showing up everywhere, but I'm going to follow one branch to highlight it because, you know, I just can't draw like 16 branches, right? So you start out with 0, and then you have a 1 immediately because of the epsilon transition, right? And then you read the bit 1 in both worlds. And here you end up back in 0, and here you end up in 2. All right? And now you see 1 again, but this guy needs to branch, a lateral branch. Right? Because 0 has an epsilon edge, so every time you see a 0, it gets replicated at the same level immediately. And you read 1 again. You go to 2. Okay, here you go to 3. And a lot of stuff happens here. Let me not draw all of that because I think it's going to get messy. Okay, and if I see one more 1, this is going to go to 3, this is going to go to 4, and one more 1, this goes to 4, and this branch is dead, right? Because there's no outgoing edge of 4, that branch has been cut off. And the accepting condition only depends on what are the states that you are in at the very last layer, right? So what happens before is not important. You might have been in accepting state before, but if it was in a dead branch, that goes away. Okay? So accept. All right, make sense? You can do it, hold on. So you can do other examples, but the intuition is that the epsilon transition is kind of telling you're guessing, okay, I'm within the last 3 bits and I'm going to start branching. Okay? That's the intuition. Any question?
Yeah, technically speaking, all the transitions of 2 and 3 and 3 and 4 can, we just get rid of the ones.
Yes, we can. We can get rid of 1 state here. This is not the most efficient NFA. You can have 5 states here. You can make 4 states as well. And you're also right that I can maybe get rid of the ones there, but I'm not trying to be very efficient. But that's definitely true. Yeah?
The idea is that like every point try to be next 3 bits, right? Next time we index the string. Then if there's something there afterwards, then it's lost. If there's something there afterwards, and that's no transition in that case.
Yeah. Any other questions? Yeah?
Why are 2 and 3
So sometimes I could have a string just 1, 0. So we said there has to be 1 within the last 3 places. Right? So if I see just 1, 0, then basically I take the epsilon transition, I see the bit 1, and then see 0, so I have to accept because I'm only going to reach 3 in this diagram. Okay? If the language was, there has to be a 1 exactly 3 positions from the end, then you wouldn't make 2 and 3 accepting, only 4 as the accepting state. Okay? And it is possible to make a DFA out of this along the suggestions that was made at the very beginning. But the smallest DFA for this language has 8 states. Okay? And has like tons of arrows. It's very complicated. I mean, at least intuitively, fairly complicated. And here I have 5 states. I can simplify it. It's just almost like a chain. It's easy to understand what's happening. If I have 8 states and then I draw all kinds of diagrams, then it's messy. Okay? This is kind of an illustration of why NFAs are kind of helping us. They allow us to guess for free and just kind of check our answer later on. Right? Imagine in the exam they have multiple choice questions, you just keep branching in 4 different rows and they take the best of the possible world that you're in. That's not a good exam, right? Maybe it is. Okay. So, any questions about how NFAs work and their power? Let me write that as a remark. So there's a question in the chat. Hold on. Does a dead state mean it stays in the last state it was in? Dead state means that the branch has been cut off. So unless you are in the dead state in the last layer, it won't count towards acceptance, right? So imagine you're kind of basically growing these chains. A dead state or something, if it doesn't have an edge out, that just means that simulation is kind of ending there in that path. And the condition of acceptance only depends on the last layer of stores. And if it helps, it doesn't really change anything. But if it helps, you can always picture there actually being a global dead state where whenever there is no arrow, you can add dummy arrows to that dead state. Okay? It's kind of, there's one branch like a black hole where nothing comes out of. You can imagine you're doing that. So like in the question, in the example, if 1 was an acceptance state, would it still be accepted? Yeah, if 1 was an accepting state, then everything, it depends, right? It would change the definition a little bit, but it could, that's allowed in the definitions. It would change the language that we're computing, but nothing prohibits us from making 1 also an accepting state. All right, so these are all excellent questions, and I think it's an illustrative example of what happens. Let me remark. There is a DFA to compute L as above, but that needs 8 states. Okay. And if I ask, one second, if I ask you the same thing, right? If I tell you, okay, my language is all strings that have a 1 in the last 4 positions, then it's easy to extend this diagram, right? You somehow have to just add one more arrow and that would work, right? But the DFA, the best DFA for that has 16 states. Like, you know, we'll see why later on. Yeah?
We used to really think about how to handle history and problems in general.
So it should be specified in the diagram. Like, you know, here, for instance, if I see the empty string, then what am I going to do? I'm just going to be in 0 or 1. Neither of which are accepting, so the program is going to say 0.
So like an example, we're given a policy create an NFA, if it doesn't say anything about unstring data, it's rejected.
Yeah, definitely. Yeah. Any other questions? Okay. All right. So far everywhere, you know, NFA seem very powerful, but here's the twist in the tail. Let me throw a wrench in all the parallel worlds that you're living in. There is only one reality. The first time I saw it, it's kind of mind-blowing. But what it's saying is that every NFA has an equivalent DFA. Okay? So meaning, I wish I could play some dramatic music now. For every NFA, okay, it's fine. So for every NFA n, there exists a DFA such that n of x equals d of x for all x. Okay? So no matter how complicated your NFA is, there is still a DFA which will compute it with the same functionality. You're getting the same functionality, but it's going to be a deterministic finite automaton. All right? Isn't this kind of contrary to what we've been saying so far, right? Kind of seeing so far. Concatenation was so easy with an NFA. Clean star was so easy with an NFA. But imagine drawing a DFA for clean star, right? Where we have this epsilon loops right to the start, so which allowed us free jumps. If I'm not doing multiple worlds, how can I design a DFA for that? So today we're going to spend some time trying to prove this. And as surprising as the statement is, with the right view, I think it is somewhat intuitive. Okay? And this theorem has a lot of impact actually on practice as well. I mean, it just seems like, okay, we defined some theoretical construct and now we made it, we went back. So what was the point of defining NFAs in the first place, right? But it's much harder to design DFAs for things like, you know, clean star operation or concatenation and things like that. Going this route, we first design an NFA and then convert it back, is one of the ways that people actually use when trying to do regular expression matching and things like that, as we'll see. Okay? All right. So what is this really saying? It's saying, suppose I have so suppose I have some NFA, right? You know, I'm starting with 0 state, and then I'm branching, you know, left and right. nothing prevents the number of paths from exploding exponentially. Right? Nothing prevents it from the number of paths exploding exponentially. Maybe every time you see something, you create a copy. And then maybe every edge has every node has two outgoing edges with the same label. It can happen. Nothing in the definition prevents it. And it could also be multiple things, right? I might not just have two branches. I could have something like this. So the number of worlds we are in is exploding exponentially. And so all of these paths kind of lead to many, many different states, right? So all the choices we make in the entire execution of the program, each chain of choices leads to one state, unless it's been cut off in the final layer. And we have to check every one of these rows if there is if it's in an accepting state, right? So we accept if any one of them is an accepting state. Okay. But so in some sense, if I have a string of length n, maybe if I have a string of length 100, the number of possible paths, the number of worlds we are, like the number of nodes I see here, could be 2 to the 100. Okay? Right? There could be so many choices. But why doesn't that, how can we still make it a DFA? Any ideas? Any suggestions? So, go ahead.
We map states in the DFA to states in the power set.
Right. So the most important, that's the excellent idea. So the main idea here is that it doesn't matter how many times a particular state occurs in this chain of things, right? So imagine, in these 3 possible choices, I ended up in state 1, here I ended up in state 10, maybe here I ended up in state 13, okay? And the next set, I ended up in state 5, maybe 7, 8, 15, 7, 7, 7. Okay? I took 2 different routes, but I ended up in the state 7. So there are 4 copies of the universe where my state is the same, right? So there are in some sense 4 identical universes, right? But do I have to keep track of all the 4 things separately? No, right? Because from this point on, this branch and this branch and this branch would be exactly identical, right? Once the state of the universe matches, 2 universes matches, their evolution from then on is going to be exactly identical. Okay? So that means I just need to keep track of 1 instance for each type of universe. I don't have to keep track of, okay, there's like 4 copies of 7, 1 copy of 5, 1 copy of 8, 1 copy of 15, and so on. I just need to keep track of whether there is a universe with the state 7. Make sense? That's the intuition, and now we'll make it formal. But the intuitive idea is the most important here, that somehow multiple copies of the same universe is not going to change the end computation, right? It's redundant. If I have 2 threads doing the same computation, it's not going to change the final answer. I might as well kind of just merge them together, or just simulate one and forget about the other because it's identical to copy. Yeah? Yeah. So, I mean, I'm saying if they are the same, then we can exploit the redundancy. Okay.
How do you know that there could be like one for each like type of universe?
Right. So there need not necessarily be one for each type of universe, but I can just keep track, as we'll see, of what types are actually occurring. There is simplicity in knowing that I only need to keep track of whether or not this state is present. I don't have to keep track of how many times this state occurs. Okay. So we'll see it more formally. But the savings, the mega savings are coming from this empirical observation that if there are copies, then I can collapse them into one. Okay? Yeah?
Can you walk them if they're on different like
No. If they are on different layers, we cannot. That's important, right? Because somehow they're going to start differing in what inputs they see. We're only able to collapse them at the same level because they're going to see the same inputs from then on, right? If you think of like, timelines and stuff, right? You can imagine these layers as like time stops. If two conditions are the same at the same time, then the evolution is going to be exactly the same later on. Okay? Any questions? Any other questions? Yeah?
So you're saying that there's a finite number of possible states in the NFA?
Right, exactly. We know it is true, right? Because each state is only one of 1 through 0 through c minus 1. Okay, hence, if I have many, if the number of possibilities is like, a million, but I have only 1,000 states that I can be in, the states are going to repeat. Okay, we'll see a concrete example and we'll exploit that. Any questions about this main idea? Okay, so let me write down the punchline. Two paths at same level and in same state can be collapsed into one. Okay. So the implication of this observation, the next step in following this logic is, suppose I'm actually writing a program, right? Forget trying to design a DFA, but I'm actually writing a program to simulate the behavior of the NFA. I have these multiple branches showing up, but I'm writing a simulator, physics simulator, which is going to model all these multiple branches. And with the goal that I have to be able to tell you what's going to happen in the very end. So if I want to do the simulation, at each layer, what do I need to know? What do I need to know to kind of progress to what's going to happen to the next layer? Imagine like I'm going to create like a checkpoint. Okay. So I've seen the computation so far and I want to go to the next layer. But there are too many things, 5, 7, 8, 15, 7, 7, 7, right? But to kind of carry out the computation forward, imagine I'm going to tell, okay, I came here so far, from now on, please you carry on the computation. What should I tell that other person? What should that person know to kind of go forward from here without changing the end result? They only need to know which states have been reached so far, right? Which are the potential states all the paths are in, right? So if I know, okay, 5, 7, 8, 15, okay? These are the states that have been reached in this layer. It doesn't matter if I have 1,000,000 copies of 5, 1,000,000 copies of 7. As long as I know there is a 5, there is a 7, there is a 8, there is a 15, I can go on from here. Right? Because I don't care about how many copies there are. I only need to know whether this particular state occurs. Does it make sense? This is kind of the implication of the fact that if two things are the same, I can collapse them. So I only need to know which ones are actually existing on this multiple universes. Okay. So now we're going to exploit that intuition. For each level, we need to know what set what states have been reached at that level. Okay. So knowing this 5, 7, 8, 15 is just collapsing them. Like just as the number of copies is not important, it's not also important what order these things are in, right? When I'm collapsing the multiple sevens, I can choose to ignore the last three, the first one. It doesn't matter, right? As long as I keep 1, 7, it doesn't matter. Okay? Yeah?
Would you need a state for the empty state too? All branches are terminated.
Right. So that's like the empty state.
Right. If the NFA, all of the branches of the NFA terminated.
Right. So that's also a subset of all possible things, right?
Right.
Okay, that's a good question. We'll get to that in a second. All right. So we started with the intuition that you can collapse identical ones, and now we are saying that we only need to keep track of less information. I don't care how many times each occurs. I just need to know what states have been arrived. Okay. All right. So now we just exploit this intuition. And to make things easier, okay, right at the beginning, in our first attempt to convert an NFA to DFA, let us suppose that the NFA does not have epsilon transitions. Okay, this is just for convenience because I want to go through this in 2 steps, right? First, we'll convert any NFA that does not have epsilon transitions into like a full DFA, and then we'll kind of massage it a little bit to add in to capture even the power of epsilon transitions. All right. So our goal is we are given as input an NFA, which we are for convenience right now, we are assuming no epsilon transitions. Okay, let's call it N. So N is P comma S on C states. And we want to go from here to find a DFA. All right, which is, let me use suffixes just to be clear. Tn is the transition function of the NFA we started out with. Sn is a set of accepting states for the NFA we started out with. And we have to come up with a DFA. Let me say TD, comma SD. And okay. Let me use different colors as much as I can. Okay. Oh, there. Okay. And the number of states is not important. All we want to know is that it's a fixed constant number of states, which only depends on the original NFA. And such that d of x equals n of x for all x. Okay. So let's take a 5-minute break, and when we come back, we will use this main idea. We're almost there really. That once I only need to keep track of this subset of things that I'm evolving into and use that to build the DFA. Okay? So let's take a 5-minute break, and when we come back, we'll finish this. Okay, so during the break, what's your name? Eric? Eric pointed out to me that for this language, there is actually a DFA with only 4 states as well. And that's true. Computel with 4 states as well. But you know, I'm moving the goalpost a little, but let's say, where should I write it? Maybe. So if I define the language to be X such that there is a 1 exactly in 3rd place from N. Okay. So I'm changing the language that we looked at for constructing the NFA a little bit. And here, so for instance, 100, 0100, 011 would, this would belong to L, but 01 or 010, these would not belong to L. Okay. So I want a 1 exactly 3 positions from the N. Right? And if I were to construct an NFA for that, what do I need to do in this diagram? Insertions. So I want only to accept string, yeah?
State 2 and 3 not.
Yeah. Make states 2 and 3 not accept. Okay. So the NFA for that would just be this guy. Right? So now I only accept when there is a 1 exactly 3 places from the N. But I wouldn't accept any other string. And the smallest DFA for this will have 8 states. Okay. And more generally, you can show that when I say I want to accept only those strings where there's a 1 exactly like 5 places from the N. There is a simple 6-state NFA for that. You know, you can just create 2 more things and be done with it. The smallest DFA, you can prove it. It's somewhat complicated, and if you want, I can tell you more about it. Is we'll have 32, 2 to the 5, which is 32 states. Okay, but that's an excellent catch. I should have actually started with this example instead of saying 3. There should be 1 within the last 3 places. Okay. Any questions about this clarification? All right. Remark. Okay, we are not going to prove that, but the smallest one involves 8 states. Okay, so let's go back, right? So we're doing this NFA to DFA, and we have an NFA with some transition function, and we want to convert it to a DFA. And I'm throwing out this powers of 2 for some reason here, and we kind of already identified the main idea, right? Which is we need to only keep track of the set of states that we reach. There's a question, shouldn't 2 be the accepting state, not 4? No, 4 should be the accepting state because you only accept when you're at the very end. Okay. All right. And so we only need to keep track of this set of things that we are going to reach within a level. Okay. So now if I have to build a DFA, to build a DFA for the NFA, what should my potential states of the DFA be? What should they correspond to? So what's the problem with DFA? There's only one branch, right? You know, I somehow only have one computation going on, which keeps track of some amount of memory. It keeps keeping track of some things, but only one possible exploration sequence. But within that one exploration, I want to keep track of all of these branches. So what should that one thing that I should keep track of be? Any guesses? Any suggestions?
Elements of the power set.
Right, because I need to keep track of the set of states that I have reached, right? And for the next step also, I need to know which things are potentially going to occur in the next level. I don't care about how many times. All I need to know is whether this particular state occurs or not. Okay, so let's do that. So states of the DFA, of the new DFA, B will correspond to subsets of the states of the NFA. Okay. So NFA states were on 0, 1 through C minus 1, right? So the DFA states will be subsets of 0, 1 through C minus 1. So which is the power set of C. Okay. This may be a bit confusing. You know, initially when we define DFA, the labels of the states were 0 through some number, right? Depending on how many of our states you have. But for clarity, I'm going to index them to subsets directly instead of numbers. It doesn't change the computation. Like, you know, whether I call a state A or the number 10, like, you know, as long as I define the transitions consistently, the name of the state is not important, right? So that means states of the DFA will be, you know, something like the empty set, maybe set 0, set containing a single 1 to C minus 1, maybe 0, 1, 0, 2, so on and so forth. Okay, all possible subsets of the original collection of states is a state now. We are kind of storing this entire information as one state. Okay, so how many states would the new DFA have? How many subsets are there of 0 to C minus 1? 2 to the C, right? So the number of states of the DFA is going to be 2 to the C. Okay, so any C state NFA, we are converting it into a 2 to the C state DFA. So we are exponentially blowing up the number of states, but it will still be equivalent in the sense that if I think of the number of states as a small constant, like maybe 4 or 5, it's still going to be a constant independent of the input string that you're going to parse. Right? The input string that you're going to run through, the number of states doesn't depend on that. It's finite. That's the main thing of the DFA. Yeah? Yeah, that's definitely possible. There might be a lot of redundancy here, and unfortunately, in the general case, you cannot say too much, as we'll say a little bit later. But that's definitely possible for some things. Okay. Any other questions? So we just did step 0, which is to understand what are the new states going to be. So now I have to specify the transition diagram, right? That's the transition function of the DFA. Okay, so the transition function is going to be, it's going to take a DFA and then it's a mapping which takes an element of the power set of C, takes a subset and a bit, then outputs something in the power set. Okay, so this is what the transition function should be, right? The transition function takes the name of a state, a bit, and then outputs what state you're going to land in. So it's going to take a subset, a bit, and then tell you what subset you're going to be in. Right? And the intuition is that this subset should correspond to the names of the states that you see in a level. You know what? Let me do something like this. Scribble together is great. So are vector graphics. Okay. Well, maybe this is too small. Okay. So we're going to keep track of this set of states that the NFA is going to reach. Right. So here it's 1, 10, 13. Maybe here it was just 0, and then here it's something else, like maybe it's 3, 4, 6. Okay. So if let's say this was 3, 4, maybe this was just 6. This is just 4. I'm just making this stuff up, right? For as an example. Okay. If this is what the diagram looked like, then all of these parallel paths would collapse just to 3, 4, 6. Okay, and we want our transition diagrams to respect that. Maybe you're reading bit 0 here. So now when I read 0, I need to go to 1, 10, 13. When I see 1, I need to go to this particular state. Okay. So you can see that this evolution here is looking linear, right? There's one chain, as a DFA should have. The NFA was kind of branching everywhere, but we're kind of collapsing and aggregating and then going one branch. All right? So I need to define this transition, right? This is the key part. This is where TD comes in, the transition function. Okay? So how do I define the transition function? Should not use red and green together. Okay, suppose I do, so I see a subset I and a bit A. what should the next subset be? Any guesses? So imagine you had 5, 7, 8, 6, 15 as the things that you are in. You read a bit 0 and now you're going somewhere else. And you define the next subset. What should it be? So intuitively, it should be the union of all the things that you see here, right? You know, it should have the names of all the states that should occur in the next level, right? So what should this one be here? Any suggestions? Yeah? Exactly, right? So remember, the transition function of the NFA itself was giving out a subset, right? So I take all elements in the set I, this is shorthand for that, all elements in I, and I take a union of all of them, okay? So this is all elements in I, and the transition function of the NFA. Okay? In some sense, you're just going to all the states that you might end up in if you were in an element of I to begin with. Okay? So, for instance, we are saying, okay, you are in state 5, you see bit 0. The NFA's transition said you go to 3 and 4. So you take the union of that. With when you're 7, you only go to 6. Right? And here you go to 3 and 6 and so forth. Okay? Any questions about the definition? Yeah?
You have two sets on each layer, one for like the edge goes from 0 and another goes from 1.
Oh yeah, for sure. So this evolution was only for a fixed input string, right? The NFA diagram that I drew here was how the computation was unfolding on a fixed input string. Like, you know, I see a 0, then I'm doing it, then I'm doing something and so on and so forth, right? You're absolutely right. In the definition, that's why we have the bit A, which changes. This diagram was what was happening on the input string 0, 1, 0. Okay? Any other questions? Right, so there's an intuitive way to think about it too. So TD of I comma A is all states that are reachable by symbol A from an element of I. Okay, so if I take the transition diagram, okay, so if I take the transition diagram, you know, the positions for I are somewhere here. What are all the things that I can reach by taking a single hop from this set I with the label A? I'm taking the union of all of them. Okay, any questions? So that's it, really. I mean, that's the definition of the transition function. So as an example, if I equals, let's say, you know, maybe let's say 7, 8, 9, TD of I comma 0 would be Tn of 7 comma 0 union Tn of 8 comma 0 union Tn of 9 comma 0. Okay. So if I was in a state corresponding to the set 7, 8, 9, when I read the bit 0, I go to the set corresponding to all the things that are reachable from the bit 0. Any questions? Okay. So that's pretty much it in defining the transition function. Now, to define the DFA completely, I need to also specify the set of accepting states, right? What things will make my DFA computation accept, right? So we defined the transition function TD. What should the set of accepting states be? What should the set of accepting states be? Any guesses? What should the set of new accepting states for the DFA be? Yeah? Go ahead. Exactly, right? So the suggestion is the set of accepting states will be all subsets which contain at least one element of the original set of accepting things, right? So if you go back to this diagram, we are keeping track of all the things that you might end up in, one of the branches are in, right? So if you keep on going like this, you'll end up with some set here. Maybe this is the set, right? And by the definition of an NFA, you need to accept, or you accept only when at least one of these last layer states is accepted, right? So you should accept when the last set you are in contains an element of the originally good states. Okay, the original accepting states. All right, that's a mouthful of words, but formally, SD is going to be all sets are such that okay, so all sets that at least contain one element of the original set of accepting things, right? So the intuition again is that we are simulating the universes in parallel, right? And we check in the end if at least one of those contain an accepting one, then we say yes, you reached a good input. So let's say 1. Okay. Any questions about this? Okay, so we converted an NFA to a DFA, and this is it for the complete specification when there are no epsilon transitions. Yeah?
But I have a question. Can you not a subset or like a set of subsets of states?
Oh yeah, it is a set of subsets of states. Sorry for the notation. It's basically, the set contains each element of the accepting, the set S should be a subset of all possible states, right? So here, it's a subset of all possible states, which are the power set. So it contains all those things, like, all those subsets R, which contain at least one element of the set of accepting states.
R is a subset of 0 and C
One, all such R, which contain a single thing, would be here. So, for example, if, maybe S, let's say C was 0, 1, 2, and S was just 0. Okay, or actually let me say 2. Then SD, right? These are the transition functions of the is going to be all sets which contain 2. So it will be 2 and then 0, 2, which contain 1, 2, and then 0, 1, 2. Okay, right? So all sets are which intersect Sn in a non-empty way. Okay, we'll do a more detailed example soon as well. Any questions? Yeah.
Is set all elements in the power set that contain at least one set.
Exactly, that's what it is. So SD is the set of all elements in the power set which contain at least one element from the original set of accepting things. Okay. So this is a lot of, we started with the basic sort of intuitive idea that we can collapse things when they're the same, and we arrived at this full transition function, which is now doing as good as the NFA, right? But we're still missing one very important functionality, which is epsilon transitions, right? So we still haven't addressed how to handle epsilon transitions, right? So what if the NFA has epsilon transitions? Okay. So intuitively, what should happen, right? Think of this diagram and how the simulation is going. If there are epsilon transitions, what should happen? Somehow you create these green parallel copies, right? When you have epsilon transitions. But how should that affect the universe, the kind of things that you keep track of on the right? Yeah?
After input, you should check to see if there are epsilon transitions. You might have a bigger subset of states.
Right, exactly. So, but just for convenience, we're not going to do it before the input. After the input, we'll just do before. Right, they're both equivalent bits, but we've always been doing epsilon transitions before we read the bit, right? So, in a sense, if you are in, if I could be in any one of these 5, 7, 8, 15, but they have epsilon transitions, I need to branch right away, right? I need to expand the possible universes immediately, okay? So that's what we're going to do. So let me define something. For a state S, which is in 0, 1 through C minus 1, let epsilon of S be all states reachable only by taking epsilon edges. Okay. So we said that, when I'm in a state, the way you simulate the NFA is you keep chasing these epsilon edges until you're not kind of adding new things. And those are all the things you create copies of right at the same spot. And that is being captured in this definition. Given anything, I keep chasing all the epsilon edges that I can. Like, maybe there's one epsilon edge, and then there's one other epsilon edge, and then there's another epsilon edge. I keep chasing all of them and put all of them in this one set. Okay? And the intuition is that I have to create copies for every one of these when I'm exploring the NFA. Right? So that's exactly what the DFA is going to do too. for a set I, subset of C, let epsilon of I equal okay. So I define what epsilon of S is for a single element. Now I'm extending the definition to a subset of states. So I have a subset of states. For each one, I case all possible epsilon transitions, kind of recursively. For 1, I have these epsilon edges. For 2, I have these epsilon edges. For 3, I have these epsilon edges. And for everyone, I have to throw in all of them into my possible universes. Right? So intuitively, what's happening is, something like this. If I'm 0 here, and maybe I read input bit 0, and I go to 1, and I go to 2. Okay, but each one of these in turn could create some epsilon branches. Maybe there's one more here, right? Each one of them could have epsilon branches, and that you have to chase down. So I guess this diagram is wrong. So let's say this is 7. Okay. So now, essentially, when I move from 0, instead of just going to 1, 2, I need to go to 1, 2, 3, 5, 6. 1, 2, 4, 3, 3, 4, 5, 6, 7. Okay. So if you want to keep track of all possible things, here I have 0, and here I have 1, 2, 3, 4, 5, 6, 7. Okay. So when I read the bit 0, I go like this. Right? So that's the intuition. So now I can finally define the real DFA. So let me box it and that has epsilon transitions. Okay, so Tn of I comma A. So it's still Td is going to be from the power set with a bit to the power set. Okay, and what is Tn of I comma A? So earlier we said we were taking every possible real edge out. Okay. And next, what should I do? I should take the epsilon closure of these things. And let's not use the word closure, but this mapping, this epsilon mapping of a set I, which outputs all the things that I might reach just by taking these green jumps. Okay. So without epsilon transitions, we just have what's inside. With the epsilon transitions, I just get everything. All right. Any questions about this? Yeah. Oh yeah, sorry. Thank you. This should be TD. Okay. And the set of accepting states stays the same. all possible elements of the power set which contain at least one element of the original accepting states. All right. Any questions? Yeah.
So if the epsilon function only returns the set only, like the state only reachable by epsilon edges, how about those?
Oh, okay. Right, so let's say all states reachable only by taking epsilon edges or itself. Including, you know, plus the status. Okay. So you always add the same element in. Okay. All the things that you are, like when you create copies, you don't forget what you were before, right? So I take the green jump, but I don't kill off the black thing. If that was not clear, I'm adding it explicitly. Okay. Any other questions? Yeah.
Just to clarify for the transition function, it's like you generate your next level state and then add that level you look at one.
Right. Yeah, we'll do an example to kind of really see what's happening, right? Because there's a lot of stuff with it. So let's do an example. I'll do a simple example today, and in the next class, I'll actually walk through the specific NFA example that we saw, right? The one that recognizes strings where there's one exactly from 3 positions from the end. Okay. I think the actual definition might seem more complicated than the intuitive thing that we had, but if you do an example, hopefully it will help. Okay. So recall one of the NFAs that we saw. I'm only going to do one with 3 states, because otherwise it's a little bit messy. We saw this example, I think, last class as an example of an NFA and what it would do. So here we have both of the computations, right? You know, one has 2 edges labeled 0. And then here we also have an epsilon edge. Okay. So let's say this is my NFA and try to convert it into a DFA. So the states of the DFA are going to be all the elements of the power set. So there are 8 possible states, right? So let me put phi, you know, okay, so these are the states of the DFA. Okay. And so before we draw the edges, one thing that should be clear is the set of accepting states of the new DFA, right? So here, the accepting state was only 0 in the original NFA, right? This is N. So what should the new accepting states be? In this 8 states, which states should be we accepting, right? all the elements of the power set which contain the state 0, right? So, it's going to be this one here. Help me along. Okay, so 0, 0, 2, 0, 1, 2, and 0, 1. Okay, makes sense? All those things which contain the element 0 would be accepted. And now comes the messy part of drawing the diagrams, right? So let's do an easy one first, and then so what is TD of 2, 0? I'm asking what should happen when I'm in this state and I see the edge 0 going out. Okay. In the original NFA, when I see 2, you just take one edge, right? Which is you go back to 0, right? So Tn of 2, 0 is just the set 0 from the diagram. Okay. So what is this going to be? This should be epsilon, all the things that are reachable from there, of this, which should be and what are all the things that are reachable from the state 0 only with epsilon transitions? So I'm at 2, I took 0, I ended up at 0, edge label 0. But now it's not just 0, right? I am allowed to take epsilon transitions. So it's going to be this one and this one. Okay, and there's no chain of epsilon transitions to follow. There's just one. Okay, so I just end up with 0, 2. Right? So what does this translate to? It means I have this edge in the underlying DFA. Okay, so the transitions in DFA kind of jumps between these subsets, right? So when I'm in the subset 2 and I read the bit 0, I'll jump to 0, 2. Any questions about this? Let's do one more, but this one, please help me along. So actually, let me try and write it here itself. So what is T of 1 and 0? What should T of 1 and 0 be? Any guesses? 1 and 2, right? Because 0 leads me here, or in one world it can reach me to 2. There are 2 possible worlds. The set of things that I could reach is 1 and 2. Okay, so the edge from 1, 2 with the label 0 is going to look like this. Okay, and technically I also need to take the epsilon transitions out, but neither 1 nor 2 has any chain of epsilon edges to follow. Right, so I'm done. And we'll do more elaborate examples next time. But if I draw this, let me just, I did all these calculations. So let me just fill them in. It's a messy, tedious process. Okay. And right? Yeah.
The action set line as well.
Yeah, we always do. So if you go back, I clarified the definition a little bit, right? Where did it go? So when I'm defining epsilon of a single element, I'm unioning it with the, right? That's a good question. Oh, one important thing. What should the new start state be? Right. So what should the new start state should be? I mean, technically we can think of just whatever the old start state was. You should start from there. But if it has epsilon transitions, you immediately create copies, right? So this should be epsilon of 0, okay? Which in our case is actually 0, 2. So let me flag that. So this is the start state. Okay. So you're starting from this 0, 2, and from then on the computation proceeds. Okay. And I think I'm missing one edge here, something like this. Any questions? So, I mean, it's a little bit involved, this conversion, but it packs a lot of punch, right? We started with a simple intuition, but now we can go back between NFS and DFS if you want to, right? And in the next lecture, we'll see some more examples of this conversion process to kind of gain insights into that. And then I'll talk about some really, like, you know, prominent, practically useful tools that use this conversion implicitly. Okay? So that's going to be very interesting. Things like, you know, grep search, for instance. If you've done any sort of hacking, you might have come across grep. The way it works is based on NFS. Okay, and we'll talk about that at a high level in the next lecture.